And that's an incredible capability that engineers are using OnScale today to train embedded AI using simulated or synthetic data.
Welcome to episode 77 of the Engineered Mind podcast. I'm your host Joseph, and on this podcast I'm talking to researchers, scientists and engineers and how their work is shaping the world around us. For this episode, I'm very excited to welcome Ian Campbell, CEO of OnScale, to my show. On this podcast, Ian and I will talk about the cloud engineering simulation platform OnScale and how it combines powerful multiphysics solver technology with the limitless compute power of cloud supercomputers. With OnScale, engineers can run massive numbers of full 3D multiphysics simulations in parallel to create true digital prototypes, digital representations of physical high-tech devices that capture the complete behavior of a device over its operating envelope. By shifting expensive and time-consuming physical prototyping to digital prototyping, OnScale massively reduces cost, risk, and time to market for R&D firms, pushing the boundaries of new technology. Ian and I also talked about the importance of simulation in engineering workflows and how to augment engineers rather than substituting them. We cover SimAI and how AI can be used and trained by using simulation data directly from OnScale. We will talk about the so-called democratization and making simulation accessible for everyone. Ian will talk about security concerns of the cloud, the acquisition of OnScale by Ansys and future plans. We will also talk about how physical prototyping can be enhanced using simulation, and a lot more that engineers need to know when getting started using simulation. And now, ladies and gentlemen, here's my podcast with Ian Campbell. Hey Ian, welcome to my show.
Hey, Joseph. Thanks for having me.
Yes, really cool. We have been in touch for a while now, and it's really, really exciting to have you on the show today. Today we want to talk about the acquisition of Ansys, which is, first of all, congratulations to that. And obviously
Thank
about
you.
OnScale, your company OnScale, and how you founded it, what modules you're using, all the engineering nitty-gritty like SimAI, for example. But we'll come to that at a later point. Before we jump straight into the exciting topic of how you founded OnScale in the first place, can you give us like a 1 or 2 minute bio? Who is Ian? Where do you come from? What did you study? All that exciting
Yeah,
stuff.
sure. I'm an engineer. I studied mechanical engineering at a school in Tennessee called MTSU. It's kind of funny. I was using Ansys products back then. I used Ansys Mechanical and Fluent to design a solar vehicle for the MTSU team that we competed in. I competed in Kansas. Then I went to industry for about a year. I was an automation engineer, so I was designing automated assembly lines for a company in Nashville, Tennessee. These automated assembly lines would make things like anything from an automotive assembly, like an axle, to pharmaceutical products, packaging pharmaceutical products, to making smartphones. This was back in 2005, so they weren't really smart back then. But then I decided to go back to school and earn a master's of engineering and an MBA from Georgia Tech. And I was really excited to get accepted to Georgia Tech and join an aerospace lab there called the Aerospace Systems Design Laboratory. And that was a great experience because I got to literally build and fly UAVs and got to see the whole process of designing and building one of these machines, all the way from laying up carbon fiber to building the mechanical structure, fine-tuning the propulsion system, programming embedded systems to fly the thing. So that was a really great experience. And that kind of gave me the engineering and innovation itch, and it's an itch that never went away. When I graduated, I actually went into management consulting. So I didn't touch engineering for like 2 years. And it was like the probably lowest point of my career, just from a boredom perspective. I got really bored doing management consulting, and I, wanted to use my engineering skills and my business skills to start a company. So actually, I started two companies, a robotics company and a kind of a consumer electronics company that didn't go anywhere. And then together with my a friend of mine from Georgia Tech, PhD student, we started a company called NextInput. And NextInput makes MEMS force sensors for touch applications. Turns out we had a pretty novel approach to touch and force sensing. So we started the company at Georgia Tech. We were part of the Advanced Technology Development Center, Georgia Tech's incubator. And we're trying to raise money and constantly running out of money, as startups do. And then fortunately, we were able to meet some really great Silicon Valley investors that brought the company to California. And that's how I got to Silicon Valley in 2013. And NextInput was very successful. But it was successful in spite of our engineering tools. We were still using ComSol, Ansys, SolidWorks simulation, Cadence, you name it, we probably used it. We also built a bunch of our own simulation tools and our own physical models to design our sensors. And we were running all of this engineering analysis on desktop computers. And I remember one time we tried to set up an AWS cluster to run some simulation software. I won't tell you who the vendor was, but our rep called us up and said, "Hey, I just noticed that you're supposed to be in California, and all of a sudden you've got a computer in, I think it was North Carolina, it was an AWS data center running this license, and you're not allowed to use that license outside of your site." So we got our hand slapped for trying to run cloud simulation back in probably 2014, 2015. So anyway, that's kind of where the idea for OnScale began. But that's really my background. My background is engineering, inventing stuff, taking it to market, and building successful businesses.
Cool, super interesting. Could you now maybe jump to OnScale? Like, what is OnScale in the first place? How does it facilitate work for engineers?
Yeah, sure. So, part of being an engineer, I asked myself, why don't we have cloud simulation? Why can't I go create a massive AWS cluster and run a bunch of simulations in parallel rather than running them serially on a desktop computer? Because as you know, engineers never want to run just one simulation of a design. You want to look at lots of different permutations of that design. You want to do design space optimization. You want to do multidisciplinary optimization. You want to look at multiphysics to perfect a design before you go spend a lot of money making something. That whole process is what we now call digital prototyping versus physical prototyping. And if you include digital prototyping in your R&D process, you can massively reduce risk, cost, and time to market. That was our thesis for OnScale. And the other thesis was, now that real cloud high-performance computing, cloud supercomputers are available, now is the time to create a true cloud simulation platform. Cloud HPC wasn't a thing, pre-2015. You couldn't go get a 96 core bare metal machine from AWS, and you couldn't combine a bunch of 96 core bare metal machines together on a Kubernetes cluster to make a supercomputer in 2015 or 2016. But now we can do that. So you asked about what OnScale is. Fundamentally, OnScale is a cloud simulation platform that has a cloud supercomputing layer at its hardware layer. It has a solver layer. We've built our own solvers, and we also use third-party solvers, and very soon we'll be using Ansys solvers on the OnScale platform. And we can sequence these solvers together. So we can run a mechanical simulation, and then a fluid simulation, and then an EM simulation, because we've containerized each of these solvers, and that allows us to use them when and where they're needed in the simulation workflow. So that's a solver layer. And then the top layer that you see as an engineer is you see the UI. You see a very nice, easy to understand 3D point and click simulation environment. And if you want to go a layer deeper, you can open up what we call Sim API, which is an API. It's a Python-based API that drives simulations and drives simulation sequences. And our philosophy is that you, as the engineer, you shouldn't have to worry about what type of hardware you're running on. All you care about is getting great data from your digital prototype or your simulation study. And I like to say that you could give an engineer a crystal ball, and if it gave him good engineering data, he would use it and he wouldn't care how it worked. So that's the philosophy behind OnScale. We don't tell the engineer what type of instances we're running on AWS. Instead, we look at how the engineer has set up the simulation, and then our AI that we've trained on millions of simulations will go and select the appropriate hardware to run that simulation in the most cost-effective and time-effective manner. And all we do is we charge the engineer for the compute power, the core hours associated with running that simulation. And we tell the engineer up front how many core hours that simulation study will cost him before he hits run. So that's what I mean by a true engineering simulation platform.
I really love that, Ian. Also the aspect of like using SimAI, using artificial intelligence to actually augment or enhance engineering workflows instead of saying we disrupt engineering workflows and like substitute engineers in the first place. So I really love that aspect.
Yeah.
And we'll come back to artificial intelligence in a few minutes. When it comes to OnScale, what I imagine always is that the workflow of engineers per se is not really like a constant when we imagine a plot. It's rather like fluctuating behavior over years, over weeks,
That's right.
over time. So
yeah,
maybe you can talk about that aspect, like actually having something available at your fingertips on the cloud, and how that actually enables engineers whenever they need the cloud, they can use it. If they don't need it, they don't use it. That's really a beautiful thing, I think.
Yeah.
Maybe.
That's a really nice thing about being able to run on the cloud and being able to grab the compute hardware that you need on demand. So part of OnScale means on-demand and scalable cloud engineering simulation. So the on-demand piece means if you're an engineer and you're at that point in your project where you've defined some requirements and some constraints, you're ready to start building some digital prototypes to prove out a theory. That's when you need the cloud simulation power. And then you'll go run a bunch of simulations, you'll get a good design, and you don't need the cloud simulation power for a little while. You go and make a physical prototype and validate your design. And then maybe you see some areas for improvement, so you'll go back and restart that digital prototyping process again. So you're right that the workloads are very spiky throughout the year. They're project based, and I'll also say that when you want the simulation power, you want lots of it. You want as much as you can get because you're always under a time constraint as an engineer. You probably have a boss that's coming and yelling at you and telling you that we need to get these designs finished. He's under a lot of pressure to get stuff to market fast. So I've never heard an engineer complain about having too much time to get the design work done. It's always the opposite. So that's one great thing about our model is that you basically pay for what you use when you need to use it. And if you need to buy more core hours, it's very easy to just purchase more core hours for a project, and then don't use it when you don't need it.
Mm-hmm. While we're speaking about that, Ian, can you talk a little bit about licensing? Because you also have a free option, if I'm not mistaken. So even students or academic users who want to jump into OnScale, into engineering simulation, and not use their old, outdated laptop, because that brings me back to my uni times when I run an Abacus simulation.
Yeah.
I would just run that simulation and couldn't do anything else. So I would have to only run that simulation, nothing else. Maybe you could talk a little bit about licensing aspects.
Yeah, it would lock up your laptop completely, so you couldn't do anything else. Yeah, that's another big problem that we solve. And you're right. We have a free version. We have tens of thousands of free users that run simulations every day, and we want them to do that for a couple of reasons. One is they prove the power of OnScale to themselves without us having to like sell and market OnScale to them. That's the best way to sell a market, is just to give somebody a tool, let them use it, see the value in it. I could spend, lots more money on marketing and sales efforts and, not get any additional sales because of it. But, that one thing is what really drives OnScale sales. And the other reason we like to have free users is because they're training AI behind the scenes. They're training our system to get better, to be better predictors of, how much a simulation will cost, what type of hardware we can use, what mistakes they run into. Because, as you know, engineers, when they're getting started with FEA and CFD, a lot of times they're not, and I don't think they should be FEA experts. An engineer shouldn't have to be an FEA or a CFD expert to be able to get his or her work done. And with our AI, we can kind of see where simulations fail or where an engineer doesn't get the answer he or she's looking for. And that goes back into our AI to help guide the engineer to the right solution. So for those couple of reasons, that's why we like the free account, and that'll be a thing that persists after this Ansys acquisition.
Really cool. It also brings us to the point of democratization, how some people call it, of engineering simulation, even in the cloud. Where do you see the pros and cons of the term democratization, also in terms of like the expertise of the engineer? And as you just mentioned, the engineer doesn't have to be an expert, really, like spending 5 to 10 years on FEA or CFD to actually use your tool. Maybe you can talk a little bit about that.
Yeah, it would be tough for me to think of a con for democratizing CAE. I'll try to think of one. But the pros are there's a lot of stuff that is brought to market that's engineered that doesn't use engineering analysis. I learned that. I was kind of shocked when I got into the MEMS industry, just how many MEMS devices were designed and different iterations were launched without a whole lot of engineering analysis. It was just sort of gut feeling, and it's also the training that the generation before us had. Engineers that were kind of at retirement age now, they knew how stuff worked because they've been in the industry for 30, 40, 50 years. But with the pace of innovation, that's no longer sustainable. You can't have, the wizards, as I call them, that like know how a device works intimately, be the only ones that are bringing innovation to the market. You have to democratize innovation, and that's exactly what we're doing. And the way to democratize it is to give people easier access to simulation capability and digital prototyping capability. And imagine if you could take a young engineer and simulate a device to such a high degree of fidelity that engineer begins to understand the physics that are going on behind that device and understand how external factors will affect the performance of a device. Like at NextInput, we were designing sensors, MEMS sensors. So we're trying to optimize for size, which drives cost, SNR sensitivity, power, performance. We had all these different conflicting engineering requirements. Because if you make something smaller and you make it more sensitive, you're also going to make it more sensitive to external noise. So how do you deal with that? So we kind of learned how to do that from doing our simulation work and our digital prototyping work. And I don't claim to be a MEMS expert, but we were able to get novel, new, patentable devices in a fraction of the time that it took other MEMS companies to get to market because we were using simulation. So I think that's really what we're democratizing, is innovation.
Mm-hmm. Do you feel, Ian, that there's sometimes maybe a bit of a pushback? Maybe you can talk a little bit about the statistics on how many engineers are actually using engineering simulation in the first place, like CAE tools, and then how many of those use simulation in the cloud? And also, do you feel that there's a pushback from the older generation saying, I'd rather use my calculator on the desk to do a bit of simulations and hand calcs,
Yeah,
Yeah, maybe they're a bit hesitant or resistant to move to the cloud.
that's a great question, and I actually don't have the statistics offhand. Uh, if I had to guess, I would say a small fraction of engineers actually use simulation, and I think that's a shame. In most companies, there are a group of engineers that are the simulation engineers, and they're usually almost like a business unit. And you'll have designers and other engineers that are working on a problem, and they're physically prototyping to solve this problem. And when they get stuck physically prototyping, you know, building something, breaking it, figuring out why it broke. That's kind of the classic engineering process. When they get stuck, they'll go talk to these simulation experts who are usually like in an ivory tower, and they're very busy because they're always running simulation analyses for the engineering groups. And it's tough to get on their calendar, and tough to get help from them. And I think that's what we're trying to solve with democratization. If we can get simulation into the hands of even CAD designers. Ansys had this product called Discovery Live, which I think was incredible, where you could, as a CAD designer, you could be designing a bracket or something, and you could get instant feedback on whether that bracket is going to work or not. And then you go back to the drawing board and iterate very quickly so that, ultimately you're going to give that design to an engineer to analyze it, but you've cut out a bunch of the iterations with that engineer by getting as close as possible to a working design at the design level before it goes to engineering. So I think the more that we can couple design and engineering together, and the more engineers that can use simulation, and the more engineers that can use cloud simulation, I think we're going to quicken the pace of innovation. I'm really excited about that.
It's really cool. And I think you said something which is also very interesting. Maybe we should actually talk about it a little bit more, which is the collaboration aspect. So when you have a design team and an engineering team, making them actually communicate, let's say we call it the COVID, how you call it the COVID-19 effect during the pandemic,
Yeah.
how do you actually communicate results, share CAD files, share simulation results? And that's actually something that's embedded in OnScale.
Yeah, it is embedded in OnScale to be able to share a project and to share templates even. Our ideal workflow, or my ideal workflow as an engineer, would be, I start in a cloud CAD tool like Onshape, which is the best cloud CAD tool out there right now. It's the former SolidWorks guys that started that company. I was a huge SolidWorks fan. Now I'm a huge Onshape fan. And you design a part in Onshape, and you may not know, as the CAD designer, you may not know what the optimal configuration of dimensions, material properties, etc. are, but you can get pretty close. And you're designing this part, and then in our ideal workflow, you seamlessly integrate OnScale with that. You can send it to OnScale. You can send all the parameters. You can create a parametric simulation study from that piece of CAD. Within OnScale, you can look at different material options. You can parameterize the CAD. You can basically find the right combination of geometry and material properties that solve the problem. And then you can bring the winning design back into Onshape and tag it in Onshape's PLM, product lifecycle management system. And you have all the simulation data tagged as well. So if your boss says, hey, why did you guys design the part this way? You can say, well, here you go. Here's a presentation of all of the simulation studies that we did, the analysis that we did to prove that this device will work. That's a highly collaborative capability, because within Onshape, I can share my part with different engineers. They can comment on it. They can actually put in 3D tags to tell me, hey, make this fillet 3 millimeters instead of 5 millimeters. Within Onshape, same thing. I can collaborate with other engineers. I can say, hey, have you thought about this boundary condition or this physical effect? Have you done a thermal analysis on this part instead of just a stress, strain, displacement, static mechanical analysis? So, and by the way, you can do all of that without ever emailing a file to someone or saving a file on your local desktop and having to wonder if this version of the file is the latest version that that corresponds with, these simulation results. Because it's all in the cloud, everything is tied together, and you've got, a complete revision history of what you've done. Even if you have to roll back to a previous version, it's very easy to roll back as well. So that's an incredible capability.
Very exciting. And as we mentioned in the beginning of the podcast, you were acquired by Ansys. So actually, OnScale will augment Ansys cloud portfolio by providing this cloud native, as you called it, web-based user interface for engineering simulation. So maybe you can talk a little bit about that. I have so many questions. Maybe we can just talk about how that even came along in the first place.
Well, like I said, I mean, I'm a huge Ansys fan. I've been an Ansys user for my entire engineering career as well. And we got a very nice introduction from one of our advisors to the Ansys folks. And, they were aware of us, aware of what we're doing, and aware of our vision. We had a few conversations first about, whether we should partner. And then they called me up and they're like, you know what, we could do a partnership thing where we give you some solvers and you put them on OnScale, but I think it would make a lot more sense if we just acquired you guys. And I was like, all right, let's do it. And I think it's exciting. It's exciting for a number of reasons, but the thing that gets me most excited is I think we put together the world's best cloud simulation platform with those layers that I mentioned earlier. And, now our solver layer, which, to be honest, that's one of the toughest things to do, is to create good solvers that are accurate, that have lots of different physics features. That solver layer will be augmented by the solver IP from Ansys, and they've got the world's largest set of solver IP. They've got every physics solver you can imagine, Joseph, like every type of FEA, lots of CFD, electromag, fatigue, just lots of really cool stuff. And if we can get all that stuff to play together very nicely on the OnScale platform, it's really going to be a game changer for engineers in the near term. So that's why we were mutually excited, Ansys and OnScale, and that's why we decided to do this acquisition. It really accelerates cloud engineering simulation, and I can't wait to see what engineers will do with this capability.
Yeah, really excited, really pumped to hear that. Actually, like really happy for you guys, and looking forward to see what's happening in the future. When we talk about the future, Ian, you talked a little bit about it. Are there any plans already with that collaboration? Anything we can expect in the near term?
Well, I don't know if you can tell, but I'm actually in a hotel room right now in Canonsburg, Pennsylvania, with the Ansys folks. And another really nice thing about being here is it's my people, it's our people. They're all engineers, they're all solver, computer scientists. It's really great, an awesome team, and we're fitting right in to that team, and they're really embracing our team and giving us all the support that we need, which is great. But I don't have anything to report in the near term. Part of my job this week is to work with the Ansys thought leaders in different simulation categories and create that plan. And we'll make some more announcements very soon about the roadmap and when you can expect to see some Ansys tech running inside of OnScale.
Good answer. Good, safe answer. I hope I would get something out of here, but not this time. Yeah, but hopefully we'll see something.
We could talk in 6 months, and I'll have a lot more to tell you.
Sounds good, Ian. Like right now, can you maybe talk a little bit about the solvers that are currently implemented in the backend of OnScale? Like, what can engineers use when they start with OnScale?
Yeah, sure. Today, it's our solvers and a couple of third-party partners that we've integrated with. Our solvers are FEA solvers. They do basic static mechanical. We're rolling out some contact conditions, advanced contact conditions. We're rolling out a capability to look at an on-shape assembly and understand the connectors and contact conditions between a multi-part assembly, and allow the engineer just to go through a checklist to say, yeah, this is a Revolute mate in on-shape. It's going to be this type of boundary condition in OnScale, and do all that automatically, which I think would be really cool. And then we've also, from a physics perspective, we've also got thermomechanical. We'll be rolling out some nonlinear and dynamic physics very soon that will eventually enable things like digital drop testing solutions. So that'll be really cool. And then with our third-party partnership, we've got access to a really awesome LBM solver that will eventually be able to do all sorts of fluid flow simulations, multi-phase simulations, internal flows, external flows. It's going to be useful for a lot of different things. And then, our goal is to just keep adding physics capabilities, both in our own solvers and then now kind of picking and choosing the best Ansys solvers that our customers want. Everything that we do is going to be customer driven. So if customers are asking us for a particular type of physics, we'll go look at the Ansys portfolio and we'll start integrating the physics that our customers are asking for.
Really cool. Really like that. You talked a lot about testing in this podcast, Ian. When we think about digital or actually testing in the real world, physical prototyping and generating prototypes, how do you see simulation reducing this prototyping aspect in the future?
Well, I kind of talked a little bit about the old school way of engineering, which was design something, build it, break it, figure out why it broke, go back to the drawing board, build it again, and keep iterating on that physical prototyping process. And that's hugely time consuming, hugely expensive. It's risky. We think that digital prototyping, and not only digital prototyping, but things like digital qualification, digital verification of a design before you go, make your first prototype, will cut out 90% of that physical prototyping cost, time, and effort. And that's not just me saying that. You can go read some white papers from some of our partners like Philips Medical that, they say they used to have this sort of physical prototyping process. And there was some simulation up front. They would do some, basic simulations to try to optimize the medical device. But then ultimately, the quote unquote real engineers would take over and they'd start this physical prototyping process. They switched to a digital prototyping process and they cut out something like 90% of the cost, time, and risk from their product development cycles. So I think we'll see that more and more. And I also think that in new emerging areas, you won't be able to design products without simulation. An example of that is how Tesla is simulating cars moving around in a virtual world to improve their ADAS systems and actually generate data sets to train AI. And they're using simulated data to train AI. And that's a really exciting new capability.
Mm-hmm. I think it's funny that you mentioned Tesla, because earlier in the podcast you said that all the engineers that are building those simulations or performing simulations in OnScale, they actually train your AI in the background, which is kind of like the Tesla field, which is collecting data and improving the algorithm. So you have your fleet of engineers all around the world using OnScale and actually improving the AI, which is super cool. When we talk about artificial intelligence, maybe we'll stay at that topic. I think 2 years ago, there was even 1 or 2 years ago, you announced something called the estimator, where you said you take its input parameters, like the degrees of freedom, the physics that's actually running, what the output was, or what you could predict was something like the runtime of the simulation, core hours consumed.
That's right.
When we look at the roadmap, Ian, where does AI, or what does AI sit in the future, and how does it augment engineering workflows?
Yeah, it's going to be a really exciting time for engineers because they will be able to leverage AI as AI becomes democratized. And I see cloud engineering simulation as a driver to be able to use more AI in your engineering processes. An example is what I just told you about, how Tesla's using simulated cars driving around in a simulated environment to collect data sets to train their AI. But on a more physical level, we have customers that are using what we call sim AI today, not to be confused with Sim API, which is our simulation API. But Sim AI is the concept that, let's say you're designing a sensor. Let's say you're Ian Campbell at NextInput, 10 years ago, designing a sensor for a smartphone. And first of all, you've designed your sensor, so you know what the sensor looks like. Then your next goal is to put it into a mechanical assembly. And that mechanical assembly is going to be, there's going to be mechanical and manufacturing variants and how that assembly is created, in production. So we have to account for all the different manufacturing variants that is going to affect that sensor. And there's also going to be environmental variants. Once we put the sensor into something like a wearable, it's going to be out in the environment. It's going to heat up. It's going to cool down. It's going to experience shock, vibration. And our sensors have to be robust against that. And our algorithms have to be robust against those different environmental changes, and manufacturing variants. So how do we design these algorithms? Well, one way, and this is what we did at NextInput, we just built a bunch of prototypes and we tested them through rigorous physical testing. We would put systems into environmental test chambers. We'd take them up to 80°C, down to negative 40°C. We'd inject humidity. We'd put them on shock tables, vibration tables, and get a bunch of data, physical data from the sensors. And then we'd use that data to train the algorithms to correct for those different signals so that we could detect the signal that we wanted to detect, which is a human figure on the touch surface. That process that I described for you was, it took us years to do that, to collect that physical data. Now with OnScale, you can just simulate all of those different things happening. You can simulate the manufacturing variants. You can create a million different digital prototypes that reflect the entire distribution of manufacturing variants on a product. You can test all of them, simulate all of them. You can take each one of those and you can put them on a virtual environmental chamber, heat them up, cool them off with thermal analysis. You can put them on a virtual shock or vibration table, subject it to shock and vibration virtually with simulation. And then you can create this massive data set that then you can then use to train your first AI algorithm. And then the moment you make your first prototype, you put that AI algorithm on the first prototype, and guess what? It magically works. And that's an incredible capability that engineers are using OnScale today to train embedded AI using simulated or synthetic data.
This is really incredible. I really like that approach and how you actually see AI as rather an augmenting technology rather than actually substituting the engineer, as we mentioned earlier on in the podcast. And of course, if people want listening to this show, we can also have a demo on my channel in the future. And I will link to a talk from Ian where he actually talked about this MEMS application and how AI is used in terms of how the neural network was built and what kind of layers were used, if someone is interested in that. When we think about testing, you mentioned like that testing can be reduced up to 90% using simulation throughout the product development process. Of course, we have the remaining 10%. Do you believe, Ian, that testing will become redundant in the future, or do you still believe we need tests, like physical tests in the future?
That would be a very, very bold statement to say that simulation could completely replace physical testing in a product design lifecycle. I could see in the future how, with cloud simulation, cloud supercomputers, AI, and fantastic engineers that are driving all of this, that you can get very, very close to launching a product without, with doing a minimum of physical testing. But it's hard for me to imagine a day where like you would feel comfortable enough launching a product that had actually never been physically tested. It had only been simulated. And it just goes out into the world in millions or billions of units. I think it'd be cool if that happens. Maybe it does happen one day, but I think at that point that's like, that's Jarvis if you're an Iron Man fan, or it could be Skynet if you're a Terminator fan. But that's the direction things are going. So I prefer to imagine the universe in the future as one where we have a Jarvis, a supercomputer with AI that understands multiphysics that's helping engineers get stuff done. And I think we're going to make that happen with this OnScale acquisition by Ansys.
Love it. Love the optimism. Also, when we talk about the future or the status quo, we all move to the cloud. The cloud is great. We use Google Docs. We use OnScale. We use Onshape, for example. But there's still a bit of pushback when it comes to the security, like the concerns of security in the cloud. Can you maybe talk a little bit about that? Maybe take away the fear a bit from all the people listening to this podcast, thinking if I go to the cloud, I'll lose all my data and whatnot.
Yeah, I used to have this conversation with mainly CIOs at organizations because their job relies on keeping things secure and to some extent keeping things on premise. I think so much of the world has gone to cloud. It's kind of silly in some respects why engineering simulation hasn't gone to the cloud in a more meaningful way. Like you probably do all of your banking on the cloud. You probably have lots of other accounts on the cloud. You said you use Google Docs, so I'm sure you've got lots of intellectual property in those Google Docs, and you trust Google not to have a breach and people stealing your Google Docs. You trust whatever bank you're using not to have a breach and people stealing your money. What I used to do just to be kind of tongue in cheek with these CIOs is I would ask them, how many armed security guards do you have outside of your on-premise data center? And they'd say, well, none. And I'd say, well, at Amazon, our cloud vendor, they have armed security guards that are protecting their data centers. Moreover, if you wanted to steal data from an Amazon cloud data center, you can't do it from the outside. You can't hack into it. AWS has never been directly hacked. People that build apps on AWS, and if they don't do it the right way, they can have security vulnerabilities and get hacked. But we have an entire team that focuses on SOC 2 compliance and penetration testing, and we work very closely with AWS to make sure we're adhering to all of their security standards to make sure we can't get remotely hacked. And then the only other way to get data out of a Amazon data center is just to try to physically get inside. And even if you were to get inside, let's say you're a ninja, and you got past the armed security guards and you got inside an Amazon data center, it's rows and rows of computers. So you have no idea what computer is running what computational workload. Whereas engineering companies with on-premise data centers get physically hacked all the time. A disgruntled engineer will walk into a data center, put a USB stick into the on-premise data center, pull off the data, and go sell it to your nearest competitor. That happens every day with on-premise data centers. That would never happen with AWS and our solution.
That makes a ton of sense. Cool. Two remaining questions, Ian, for you. One would be, as a visionary of engineering simulation, what is your vision for the future of simulation?
Well, near term, my vision is to work with our new Ansys friends and get as much simulation capability as I can into the platform and make it incredibly useful. And I want to make it so that newer engineers, that the next generation of engineers will be so comfortable using cloud simulation that they would be uncomfortable going back to trying to run simulations on a laptop like you did and having their entire laptop lock up. And it's going to be really exciting. The best part of my job is going and talking to engineers and seeing what they're using OnScale to do. And then longer term, I really think with the combination of AI, cloud simulation capability, cloud supercomputers, new hardware topologies, GPUs, TPUs, ARM processors, all this capability that's going to come from a hardware perspective to the cloud. I think engineering simulation is just going to get better and better, and it's really going to unlock innovation for engineers. They're going to design amazing stuff like next generation eVTOLs and hopefully rockets that you and I can fly into the moon, or whatever they design. It's going to be an amazing world.
Yeah, really looking forward to that. And as you said, in 6 months we'll see more from your side. So I'm really, really looking forward to that. As a last question, and as an innovator yourself, maybe you have remaining tips. Let's say 3 things you need to know to successfully build a startup. Let's put it that way. Some practical tips for our
3
listeners.
things. I think if you're an engineer and you got a great idea, go get some business education. Learn how businesses work, because businesses work a lot differently than engineering systems. Business decisions don't happen in a linear, orderly, mathematical process. They're very chaotic, and you have to be able to adapt and pivot. And so go read some books on how to start a business, or get an MBA like I did, which was an eye-opening experience, because the MBA, the way they teach you to think as an MBA student is very different than the way they teach you to think as an engineer. So that would be my first tip. And then second tip is always be looking for validation, proof points of what you're doing. This is advice that I didn't take with my first 2 startups. I didn't get the proof points. I was emotionally attached to what I was doing, so that I was very biased. I had selection bias, and I wasn't willing to take the feedback from people that were telling me basically that it's a bad idea. No one's ever going to tell you, hey, your idea sucks, don't do it. But they will tell you in a very nice way that, about all the pitfalls that you're going to encounter with, the particular approach that you've chosen. And, take that feedback and really assess it in as much of an unbiased way as you can. And then third tip is surround yourself with an awesome team. Find people that are smarter than you and more dangerous than you in areas that you are weak, and, bring them in, give them equity, get everybody incentivized and aligned. And with an awesome team, you can move mountains the way that the OnScale team did, and the way the NextInput team did. I had very little to do with the outcomes of both businesses, other than kind of like getting the idea started and surrounding myself with awesome people.
Love it, Ian. Really cool. Any closing remarks from your side? Where can people find you? Where can people reach out to you? Any last words?
Well, they can. I have an email address, ian.campbell@onscale.com. You can reach me on LinkedIn. And I've got a new email address. Guess what that is? ian.campbell@ansys.com.
Yeah. Great. Cool. I'll put all relevant links down in the description of the video. If you have any questions, put them down in the description and we'll make sure to answer them as soon as the podcast goes live. With that, thank you so much, Ian, for your time. It has been nice talking to you. And by the way, big thank you for also supporting my newsletter on that note. So personally, that's great. Thank you.
Yeah. I love reading it. Yeah.
Thank you so much. And hopefully we'll have a second session in the future, and maybe even a demo on my channel where we can kind of show what Sim AI can do. Really cool. Thank you so much. And I'll see you hopefully in the second part or on LinkedIn.
All right. Yeah. Thanks, Joseph. Talk to you soon.